And you'll see today that it is, I'm not kidding, it literally uses everything. So here's a warm-up to have you guys review something that's going to be needed for today. So let theta be the angle between vectors u and v. I would like you to remember, how is the dot product of u dot v used to tell you if theta is equal to pi over 2, if theta is less than pi over 2, or if theta is greater than pi over 2. So if you guys can maybe like try to use some of your knowledge from that topic. And see if you guys can remember, how is the dot product used to tell you the value of the angle? Not the exact value, but just those values there.
When the dot product is equal to 0, so the theta is equal to.
So that's what I want you to think about. Yeah. And then write your own descriptions here, and then I'm going to have you check in with your groups. Okay?
Yeah.
Take a look here. Let's have YouTube here. As usual. All right, guys. So how did you use that dot product? How did you know? You took the dot product, and you should be able to conclude one of those three cases. I remember that.
We also use this in
Oh, sorry guys, turn in your homework. Homework 19. Turn in your homework while you're doing your chat.
Is it 19?
I believe it's
No, I did. It's 19.
It's 19. I think it's 19.
19. Yeah, 19.
We'll give it anyway. I'm not sure about that, but probably it would make a lot of sense.
Yes.
Yeah. And was greater than pi over 2. Less than 0. Leave the way that's less than make sure you use pi over 2. So no, it's greater than 0.
Okay. Okay, guys, let's see. So let's try to remember a couple things. What was a theorem that we covered that used the dot product and an angle between them? Cosine theta u dot v over. Correct. You guys use this guy here. Okay. Will the bottom ever be negative? No, right? It'll never be negative. So it's only this guy that will make it negative. Let's assume u and v are not the zero vectors. That way you'll never get zero on the bottom. Okay. So when did we have pi over 2? What must happen for that to happen? What would be cosine of pi over 2? It would have to be 0, right? So that means this would have to be 0. So what does that tell you about the dot product? Have to be 0. So let's see. So this helped us conclude. We did a little chart like this back when we were covering it. We saw that if it was pi over 2, the dot product had to be, as you guys said, 0. What happens? What are the what type of values do you have for cosine when theta is less than 90 degrees? They're positive, right? You ended up with positive values. So these were positive. Cosine of theta had to be positive. So this had to be positive, and this is positive. What does that tell you about the dot product? It has to be positive. You have to have a positive answer. So if your dot product is positive, then this told you that theta had to be less than 90 degrees. Okay? And it has to be greater than 0. Okay, what happens with cosine of theta when you plug in an angle bigger than 90 degrees? Cosine is going to be what? It's going to be negative. So if cosine is negative, and then you have this divided by a positive, what does that tell you about the dot product? It has to be negative. So immediately from, let me put the pi over 2 here. Something that we were discussing when we did the dot product was you take a dot product of 2 vectors. If the dot product was 0, then immediately you can conclude that the angle between them is 90. And so what was the name of vectors where this happened? What do we call the vectors? The angle between them is 90. They're called orthogonal. Remember, orthogonal vectors are vectors whose dot product was equal to 0. I take a dot product and then I get a positive answer. Don't really care too much about the positive, what value it is. I know it's positive, so I know the angle between them will have to be less than 90, right? So do you see, if I do that, that means they're kind of like relatively pointing in the same direction. They're both going this way, right? Versus if I take the dot product of 2 vectors and I get a negative answer, I know their angle will have to be greater than 90. So relatively to each other, they're pointing away from each other. They're pointing in opposite directions. Not necessarily exactly opposite, but like relatively opposite. Okay? Okay. So that's from what? Chapter 12, I think, when we covered that. All right, so I wanted to put that back in your head because the textbook is going to use this fact and just have you assume you remember all those things. Okay? But I know it's been a minute. So let's talk about what a vector field is going to be. Let me show you just through a visual first. Let me show you guys some examples here. So if you ever watch the weather app or the news, they show you pictures that look like this, right? So this is in this picture here we have the velocity vector fields. Don't worry about what that is. Showing San Francisco's wind pattern. And this is back in 2010. Let me turn down the lights. And so what this was telling you is that it was showing you kind of the way the wind was moving at 6 p.m. at this date. And then here it was showing you that at 6 a.m. it was moving in a completely different direction, right? So notice like here it seems to be coming, the wind seems to be blowing towards the east, where here it seemed to be blowing towards the west. Okay, Sam, yeah.
Is there anything like the slow fields?
It is very related to the slow fields if you're taking differential equations.
Yeah,
it's very related. And so, for example, if there's an object moving, like let's say a bird, and it's flying here, we would want to know, is the bird flying kind of like with the wind? Is it flying against the wind? Is it going this way, right? So vector fields are going to be these type of functions where you plug in a point somewhere in our let's say this is two-dimensional. You plug in a point somewhere, and then the function is going to tell you the vector associated to that point. So see all the initial points of these vectors? Those are all the inputs, are the points. The outputs are the vectors themselves. Okay, which is new. You've never seen something like that. Well, you have, and I'll show you how you've seen something like that. But we haven't thought of it as a function. Okay? So far functions, you've plugged in a number, you get a number. You plug in right, you guys have seen this. Plug in a number, you get a number, right? Get a number here, and you get a number out. Then you did these things. You plugged in a number, and what did you get? You got a vector. And then we got to chapter 14. And then here you plugged in a point. Plugged in a point, right? You plugged in a point. And what did you get out? You got a number. So see, it's kind of confusing because we've been dealing with functions, but they all do something, all three functions have done something completely different. Okay? So what we're going to do with this new one is you're going to plug in a point, and it's going to output a vector that we haven't seen yet. We haven't done a function like that. Okay? And so what's the graph going to look like? Like that. For every single point, there's a vector associated to it. Okay? The application here is the wind pattern, for example. Okay? If I go down below, here's a different application of a vector field. So this chapter, even though we won't go too much into the physics, it's used a lot in physics. Okay? We're going to just study the math of it, and then I'll sprinkle in a little bit of physics there when it's appropriate. But yeah, so here it's showing you the current and the wave of motion of the water, right? Depending on a point on the water. Here we have a gravitational force field. So depending where you're at, it's showing you the force in the direction that it's going. The longer the vector, you can think of it as like there's more, stronger force pulling you there. Okay? So that's the theme of this class, or this chapter, is stuff like this. Yeah, no.
Is there like a set interval for how many vectors you have for like 2 units or something?
You mean like how many vectors get outputted?
Yeah.
Here? You would have to restrict this guy first. Like you would have to say, I only want to use points from the first quadrant. And so then that will restrict this here. Is that kind of what you meant?
Well, even if it wasn't restricted to the first quadrant, there's an infinite number of vectors that can be put there.
Totally.
So is there like a way that's like a vector at every whole number or something?
Oh, I see. Yes, yeah. So what he's saying is that technically, you see how it doesn't show vectors here? These little areas here, there's technically going to be vectors there. They're just not plotted. So every single point has a vector. So if you guys can just picture like all the infinite number of points, all of them have a vector. But obviously that's going to be too hard to see. So we usually just pick a finite number of points to plot the vectors. And I'm going to show you with visuals. Like GeoGebra and Desmos don't work for this, so I have to use something else. Okay. All right. So I just kind of wanted to motivate what this is going to look like. These will be in your chapter 16 packet that I forgot to print out, but they'll be there when you guys come back next week. Okay, so let's write this stuff down here. And let me. Oh yeah. Okay. All right, guys. So section 16.1, something called a vector field. Let's write a formal definition here. So we're going to define a vector field as a function. We're going to say a vector field, when we talk about it in 2 dimensions, R2 is a function, capital F with a vector sign on top, that inputs a point xy, x comma y, and outputs a unique vector f of, and when you plug it in here, since we're in 2D, we're going to have a 2-dimensional vector. Where you plug in the point, you're going to get a 2-dimensional vector, but then this point will be plugged in to a function that you studied in chapter 14, a function like this one. It'll be plugged into the component functions p of xy and q of xy. Whose initial point is that point xy. That's where the vector will start. Okay. These guys here, like I said, are called the component functions. Component functions are scalar functions. Like these guys, they're going to output a scalar. And then, nope. If we were doing this in R3, what do you guys think would happen? Yep, you're gonna plug in a 3-dimensional point and output a 3-dimensional vector, correct? So, and if we have f of x, y, z will now be a 3-dimensional vector that will use 3 component functions. P of x, y, z, q of x, y, z, and then r of x, y, z. What is this? Oh. Or my message. All right, and so since these are brand new kinds of functions that you've probably never played with, let's take it. Let's go to like just to the basics, and let's just figure out how to plug in a point and how to output it and how to graph it. So we're just gonna go to the basics. So let's sketch a few vectors for this vector field here. XY will be something very simple. Let's just call it negative y and then x. Okay, something very, very basic. This right here is the p of xy. This is the p of xy. And this guy here is the q of xy. It's just, we're making them very simple. Okay? So let's see. Let's go back to when you guys took algebra and let's just do a little table. What are we plugging in? Plugging in points, not numbers. We're plugging in points, and then we're going to get out the vector. And then here, I have some points to just play with. We're going to do the point 1, 0, negative 1, 0, 0, 1, 1, -1, 2, 1, and -2, 1. Just to play with those. Okay? So let's see. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so let me have you guys fill in the table. Remember how to sketch a vector. But remember that these vectors, their initial point starts at the point that you plugged in. Okay? So put these into this function, figure out the vectors that you get out, and then figure out with your group how you're sketching them. Back to the basics. The more you plot, the more you'll see kind of the flow of the vector. Yeah, these are just 2D vectors. This one is 1, 0. 2, 15. 15. Okay. Do another one. Next one is okay. What did I give you? I gave you guys -y, x. Shit. Perfect. No. So you don't want to sketch them from the origin. They start from the point that you plugged in. Let me see. I'll go around. Let me just see your guys' sketches. Okay. Zero, comma -1, this one? let's see, the y here, the y is 0, right? So this would be negative 0. But then the x is just the x. Oh, this point right here? 0, this one? Oh, you're right. I didn't. That was not one of these, huh? Yeah, you're right. Yeah, so let me bring this up. All right, guys, so hopefully these are the vectors that you would get. Okay. For example, let's look at the point, 1, negative 1. So 1, negative 1, here, that's this point right here that you're plugging in, and then it gives you the vector 1, comma 1. Remember, the component means the x moves 1, it increases by 1, and the y increases by 1. So it's kind of like slopish, right? So if I'm here, x increases by 1 and y increases by 1. So that's why I got this vector right there. Okay. For the point 2, 1, which is right here, 2, 1, I got the vector negative 1, negative 2. That means x decreases by 1 and y increases by 2. So give me that vector. Okay. What Noah was asking earlier was, this is just 1, 2, 3, 4, 5, 6 vectors that you get, right? But I can plug in like every single point here has a vector. Every single point has a vector. It's just we sketched just a few to kind of get an idea of the vector field. So here I have to use a different website called CalcPlot3D. Okay, it's a little more complicated to use. Let me share my screen. But the way it works is you select, do I want to graph a function, a space, it has everything for Calc 3. Space curve, vector fields, blah, 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 blah. So I chose vector field, and then I'm restricting my view to 2 dimensions. So here's the vector field that I just had you guys sketch. It looks like that. Okay, the more I expand out, if I make it even denser, let's say I want 50 vectors in the x direction, and 50 vectors in the y direction. See, like every point has a vector. It's just I'm restricting how many to show, because then it's kind of hard to see it. But let's just say I get 15 in the x direction, 15 in the y direction. So it looks something like that. Okay. So this vector field gives you an idea of how things flow, right? They seem to kind of be rotating in circles. Okay. Here's a different vector field, this one down here, where it's negative x, negative y, and so now this is its output vectors. They look like this. So that one seems to kind of do something totally different. It seems to kind of gravitate everything towards the origin. Everything seems to be approaching the origin. Okay. We're going to learn later on how to find what's called sinkholes, points that kind of gravitate things towards them. Okay, we're gonna learn all that cool stuff. Yeah, and then you can just get weirder. I can just change things. I can change the function. Maybe I do a cosine of y instead. Things just get crazier and crazier and crazier. Okay, so those are some examples of 2D fields. If you have a MacBook, something that most people don't know is that every MacBook comes with a very powerful program called Grapher. This program here called Grapher, and it does everything the other one does. And so here is, again, the vector field that you sketched. Okay. And here's the other one that I was showing you guys. The things are gravitating. Okay. So those are 2D. So I want to give you an example of a 3D vector field. Those are almost really, really, really hard to sketch by hand. Okay. So let me show you guys a 3-dimensional vector field. Where is my other grapher? Here it is. So in this case, for this one, let me. My knees are like another elbow, so I'm getting close to my bodies, man. So here, this is y is the p of x, y, z. This is the q function, just z, and then this is the r function, just x. And this is what it looks like in 3D. This is the vector field. Every point in 3D space has this vector here, has a vector associated to it. So now it's like three-dimensional, right? So now you're like inside. So you get an idea of the flow of things. So if this was water, kind of gives you an idea of the way the water is flowing around you. Okay. Something that's useful is you make all the vectors unit vectors. Because as you guys saw as you were sketching it, that's not necessarily true. The vectors can be very long. Let me show you an example before I move on. So here, the one that you guys drew, I can fix all the vectors to be a certain length. Okay. If I want to keep them their true distance, it would look like that. But normally you don't do that because it's like too hard to see anything. So usually you try to fix the vector's length to kind of get an idea. Okay, so just keep that in mind. Right now it looks like every vector is the same, but that's not necessarily true. We just care about the orientation of the vectors. Okay. The 3D one, where'd the 3D one go? Here it is. Okay, so there's that one. There's this one where notice the y function, component function, is always -2. Okay. So let me see. Yeah. So this one seems to kind of be flowing upwards when you're in this octant and then downwards when you're in this octant. This is a little trippy to see. Let me see if I can go like that. Does it move faster? No. There you go. Sick, right? All right, and then we got this bad boy here. Okay. Notice that the closer you are to the XY plane, things kind of seem to be, as you're approaching the XY plane from the top, you're getting this kind of rotation going this way. But if you're approaching the XY plane from the bottom, you have an opposite rotation happening. Okay? Yes. Like that. Yeah. And so the goal of what we're going to be doing, where all these integrals are going to come in, is if I go back to maybe this shape over here, whoops, is understanding that flow of the vector field. Okay, that's kind of where we're headed. Okay, I'll show you that. I'm not going to have you sketch 3D vector field. It's too hard. So yeah, let's see. I forgot to put you guys out your freaking pictures. So I'm gonna write down. I'm gonna show you guys 4 vector fields. Hopefully it lets me do it. There you go. Here are 4 vector fields, and this is your practice here. This is what I would like you to do. I'm going to give you 3 vector fields. 1, 2, 3. I would like you guys to match them. So there's this vector field. What? Okay, so there's this vector field here. There's this vector field here. Y and then x minus y. And then there's this vector field. Y and then we have x two. So all I want you guys to do is tell me which vector field graph goes with which vector field function. You can write like the Roman numerals next to it. Alright? It's hard, like I said, it's hard to sketch, so I just need you guys to keep practicing that visualization. So which of these, one of these four belongs to this one of these four belongs to that one, and so on. It's a little matching activity. Oh shit. There we go. Work that out in 5 minutes. Imagine. You might have to plug in some points on your piece of paper there. And that kind of get an idea of what the vector, the resulting vector will look like. See what it matches. For example, if I plug in a point here, is my vector that I plug into the function giving me a vector pointing that way? If so, then that's definitely it. Right, Nacho? You have any questions? Especially if you're not really sure how to match up? I think it's fine. Any questions?
Figure 2-2 is roughly right in the middle of all the points. There, start there, you go over 2 down 2. The only one that does that. Here you go over 2 up 0. So that would have to be 3 because that's the one that's kind of horizontal right there. And then over 2 up 4, the other one seems like that. Any question? I like how there's Roman numerals. Are there like Greek numerals, or is that just the Greek alphabet? Is the first one?
I don't know. I don't know the type of numerals. There's hella different types of symbols.
I know we use air vision. Have you ever looked up the actual air vision numbers? They're actually really easy to write. It's just like line with dot, line with 2 things, line with 3 things.
All right, guys. So let's see. Give you guys some time. All right, shout it out. What do you guys think number 1 is? 4. You guys think 4? Survey says you're right. All right. Nice. Number 2. You guys are thinking 3? Just kidding. You're right. Number 3, and then the last one, it's either 1 or 2. Correct. It's gonna be number 1. What were some strategies that you guys were using? Plugging in points? Any particular type of points or just any point? So mainly points in like the first quadrant? Is that what you were doing? Okay. Yeah, Dylan?
I used the point 2, 2 for all of them because that's kind of like right in the middle of quadrant 1. So it has like a nice visible arrow and an easy to see spot.
Gotcha. Okay. So that way you kind of saw if the vectors are pointing to the right or if they're pointing towards the left. Okay. No.
I set y equal to 0 and then see how x changes the value.
Okay. So basically all the points on the x-axis. Okay, cool. All right, nice guys. So part of your homework will be a little bit of stuff like this. All right, so I think you're getting the hang of what a vector field looks like and how things are plotted. So earlier I said that you've never seen a vector field, and then I corrected myself and I said, actually, you have seen a vector field. You just didn't know it was a vector field. And it has to do with gradients that we learned in chapter 14. Gradient vector field. And the reason they were so confusing is because they were different kinds of functions we've never seen. So let me remind you what it is. So recall that given a function f, let's say it's 2 variables, its gradient is, we define it to be the gradient of f of xy. You guys remember where it was? It was the partial. It was the partial, which they themselves were functions of x and y. Now, with what we've discussed, notice that it's a vector field, where the partials are the components. Okay? By definition, a gradient is a vector field. And it has a special name. We call this bad boy here the gradient vector field of f. Vector field of f. So I'm not, this part's kind of hard because I can't, I don't want to sketch too many vectors, but if we look at this function, it's like x squared y consider a polynomial, like cube. So its gradient vector field is made up from its gradient. What's the partial with respect to x? 2xy, and partial with respect to y, x squared minus 3y squared. 3y squared. So as you're writing that down, let me show you a very vector field graph of it. Oh crap, I forgot to stop sharing here. Can you see that? Yeah, okay. So the video, I was sharing my screen and I looked at it. But let me show you here, 2D. So, do I have it here? Oh, this is a 3D one. Oh, here it is. It's hiding. Okay, so here is this vector field right here. It looks like that. Okay. Let's see what do I have here. Okay. You guys remember what was the relationship between the vector field? What was the relationship between the gradient of the function, all those vectors, and the level curves? That's it, right? And the level curves of the function. Remember the level curves. The level curves were when z equaled k. Of the function. Is given as that. So for example, k equals 1, k equals 2. Remember that this graph has a surface. Okay. So here, let me just show you guys because I know it's been a minute since you've seen it. I guess here I do have to use Desmos. Let me go to Desmos. Okay, so here's the function. xy, x squared y minus y cubed. This is the surface of the function. The surface of the function. And then I wanted to remind you that when you let z equal a constant, you're looking at the intersection curves of the surface. You can see how when z equals 2, you guys see these kind of like hyperbola-ish type curve of intersections. Okay, so let me go to here and let me let k equal 2. Those curves of intersection that you see here are these curves of intersection when z equal 2. Does that kind of ring a bell? You guys remember that? So as I increase z, I was looking at those intersections. So when I go over here, as I increase z, those are the level curves. All the points on those level curves output the value k for z. Sort of ring a bell? Okay. So any point that I plug in on this level curve will output z equals 4. All the points there. But do you guys remember what was the relationship between the level curves, the point on the level curve, and the gradient at that point? What was the relationship? No. They're perpendicular. Every single gradient vector was perpendicular to the level curve at that point. And I want you guys to notice that's true. Now that we graph a whole vector field. No matter where I pick my point, notice that my vector field vectors will always be perpendicular to the level curves. It's beautiful. Okay? No matter where I put my level curves here, even if my z is negative, notice that I get the vector field vectors, which are the gradient vectors, perpendicular to the level curve. Cool, right? Okay. That's on my notes, on the PDF notes. I don't have a visual there, but it's kind of hard to sketch it. Okay. And so, let me just put that as a reminder here. Recall that for every point AB on the level curve k equals f of xy, the gradient vector is perpendicular to the velocity. Is perpendicular to the level curve at that point. And so a really fun question that we're going to answer later on is if I just made up any vector field, like this one, right? Like if I just make up a random vector field, is this vector field the gradient of a function? Like, is this the partial with respect to x of a function, and is this the partial of y with respect to y of that same function? That's a question we're going to answer later on. Okay? If it turns out that a random vector field is the gradient of a function, there's vocabulary associated with that. Okay, so we have some more terms. Some definitions here. So let f be a vector field and little f a scalar function. If it turns out that this vector field f is the gradient of little f, then we have two names, two things to say. We're going to call capital F capital F is called, it has a new name now, it's going to be called a conservative vector field. We're going to say it's conservative vector field. It's nothing to do with politics, it has to do with physics. And then little f is called the potential function. The potential function of the vector field. Okay. The word conservative here is used because this has to do in physics. It has to do with this vector field is going to, it conserves energy. We're going to look at that later when we do work. Okay? That's kind of where that comes from. And the word potential here has to do, again, with physics. It has to do with potential energy, which we won't really get into. That's kind of where those words come from and why they're called it. Okay. Questions so far? Yes. Cool. Okay. All right. So then there's gradient vector fields, and then the last one that I'm going to cover in this section are velocity vector fields. Velocity vector fields. That's like the pictures I was showing you with the wind in San Francisco and all that in the Bay Area. Okay, so for this one, I want you guys to kind of get an idea of what this is going to be like. I want you guys to consider an object that's moving in either 2D space or 3D space, okay? So consider an object moving along some path C. Okay? This is where chapter 13 is going to come in. because now we're doing curves. We're gonna say the velocity vector field, capital V, that's why. What this guy's gonna do is it tells us the tangent velocity vector. It's related, yes, it has to do with the tangent velocity vector of the object, of the moving object. So let me give you guys a visual. Okay. Let me show you, give you an example. Let's say we're in 2D. And you have, let's say, some object moving in this parabolic path like this. Then every point that you plug in from this path, let's say this is path C, you're going to get the velocity vector here of that moving object in that direction. Yes. Like that. Can you see that? Something like that. Did I sketch this one? Let's see. Give me a second here. Boop, 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 boop. I thought I had this ready for you guys. Okay. So if there were other vectors, let's say they were also kind of moving in this motion like this. Let's say they were doing something like that. The way you want to think about this velocity vector field is I have a point, let's say that's starting here, right? This tells me that this point needs to move in that direction. It needs to go this way. Okay? Now, it doesn't necessarily mean that I'll end here at the terminal point, just the way this point doesn't necessarily move here. It's just telling me the direction that it's going. Okay? So this point didn't go from here to here. It's not a displacement vector, it's a velocity vector telling you how fast to go there and in which direction to go. So if I'm here, this tells me that approximately that point will be moving somewhere in this direction. So I don't know if it'll be exactly here, but it'll be relatively there, like around that area. Then that point, this point tells me that this point will move somewhere over here, not necessarily there, but somewhere close. So as you keep doing that, it kind of tells you like the trajectory that you're supposed to go with, approximately. So this looks like the path that an object whose point starts here will have to take this path. It'll have to go that way. It has to follow the flow according to my velocity vector field. So if I pick a different point over here, of course, I'm not sketching all the vectors, but I have to follow the flow of the velocity vectors to tell me that path. That's kind of what's happening. Okay?
So in the vector fields, the single vector line doesn't really, the magnitude of it doesn't really matter. It's just the direction and the position of the vector.
To see the flow, to see like the orientation, the magnitude doesn't matter, no. But the magnitude matters because the velocity, bigger the vector, the faster you're moving there. So the speed's faster. Yeah. So if the vectors are small here, think of it as like, right now we're just seeing the flow, right? But if I have actual magnitude, the flow of this path here can go like this, or it can go like this. Right? We don't see the motion. We're not seeing the motion, but that's what the magnitude of the velocity vector will tell you is this is how it moves, but it doesn't, it's gonna tell you how it moves there in terms of speed. Okay, so let's say you have a velocity vector field, and let's say you don't want to follow this path that it gives you. Let's say I'm a rebel and I want to go. I'm a. Let's say we're on the. Let's say we're on. Let's see what can. Let's see. 2D. Let's say this is the wind picture, Bay Area picture that I showed. Right? And there's a bird that decides to do this, take this path. Okay? Well, there's a different bird, let's say this is bird 1. There's a different bird that maybe goes like this. This is bird number 2. Okay? And there's a different bird over here, bird 3, that goes like this. Okay? What we want to figure out numerically with just my tools of my hands and my brain is how can I tell, given the vector field, right, given some kind of vector field, how can I tell which bird was flowing relatively in the flow of the vector field and which one was maybe going against it? Okay? You guys can see how that, yeah? Okay. Well, that's where the warm-up is going to come in. Where I have to take that products. Okay. But let's take a break. So that's we're done with 16.1. It's a really short section. So let's take a break. Come back at 2:02, and then we're going to answer this question here of my little bird flying. So resume at 2:02. There you go. All right, let me pause this. Boop. All right, guys, so we left off with this question. You have a vector field, there's some path. We kind of want to get an idea of how is this path related to the vector fields in terms of flow and how it and the orientation. So we're going to have to use integrals to answer that question. And we're going to define a new type of integral called a line integral. Okay. If you guys look at the textbook for this section has many different types of integrals that they discuss. I'm only going to focus on the one we're calling a line integral with a vector field. Okay. They do other stuff with area, of a space curve, and all that. But just chapter 16 is so super dense, so I gotta just make sure I cover the parts that are required for the class. Unfortunately, or fortunately. Okay. All right, so here's the goal. Here's what we're gonna do. We have a path, so we're gonna say for an oriented, going back to that, oriented curve C given by, let's use a vector function R of t like you did in chapter 13, where it has component functions x of t and y of t. Let's make this a two-dimensional one, so we can do some sketching. So for an oriented curve C given by this vector function on a vector field now, on a vector field F, kind of like the picture that we have over here. These are 3 different paths of my birds here. There's 3 different curves. We want to determine if the vectors of F are following a similar path to C, along C. So I can think of this 2 different ways. I can either say, is my path flowing with the flow of the vector field? Or I can think of it as, are my vectors of my vector field kind of also agreeing with the path of C? Do they seem to kind of follow the path? Or like bird number 3, this bird's flying from the top right to the bottom left, but my vector fields, vectors are doing something totally different here, right? They're going the other way. So here's how we're going to do this. Leave some room for a big drawing here on your notebook. So assume a path C. Let's just make a path C. Let's pretend we have one. From point P to Q. Let's see, let me use green. So let's say you have, here's P, and then the path, let's say, looks like this. And here's Q. Okay, so this is the curve C. And then you got all these vectors on my board, all these vector field vectors. Everywhere. Well, I'm not going to draw that. But pretend there's all these different vectors all over here on the vector field. We're going to partition C into equal pieces. Just like we've been doing with integrals, we're going to break it up, partition it into smaller pieces. Let's say we got here, and try to make it, and by equal, I mean arc length equal. The arc length will be equal, okay? So here, and then here, and let's say here, and here, 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 here. This P is, we're going to call that T naught at time 0. Remember, this is like, we're thinking of, for vector functions, T is at time, we're thinking of here as that. So let's just call this T naught, and let's pick a random T. Let's say it's here. We're going to call this Ti. Okay? And then the last one, it's going to be Tn. Tn. Yeah. Okay. So here's what we're going to do. This is all. Let's make this R3 space curve, just to kind of have depth to it. Okay. So it's some space curve like that. All right. You guys remember what R does when you plug in a T and you get a vector? Oh shit! I put this in. Let's do 3D. Let's do 3D. Sorry for the pen folks. I apologize, pen folks. No, I'm sorry. Just put like a little Z of T there. Sorry. Sorry. Remember that when you plug in a T into the vector function, it gives you a vector, and then which corresponds to the terminal point is on the curve. Remember, you guys had that imaginary 3D marker that was sketching the curve. So I plug in a T. If I plug in T naught into R, it's going to give me this vector that goes from here, the origin, to that point. If I plug in Ti, it gives me a vector that goes from the origin to that point on my curve. Okay? And then you guys took the derivative of this guy. You remember what that gave you? Starts with the T. Gave you the tangent vector. So you took R prime, and then you plugged in all these T's, you plugged them into R prime, and they gave you all these different tangent vectors like this. Let me make this one a little bit more tangent. They give you all these different tangent vectors. where this tangent vector here was r prime of t naught. R prime of t naught. And this tangent vector here, this blue one here, is r prime of ti. This guy right here. The orientation of the curve, remember, goes from P to Q. So that's why it's pointing that way. Okay? Let's see. Oof. I really need this guy to wake up to that. Okay. Let's see. Okay. Running out of colors. Okay, it's okay. These are the tangent vectors, right? Then you have the displacement vectors, which is the vector that connects this point to this point. Then you have these displacement vectors right here. We're going to call them delta R. Yeah? Delta R. And so, for example, this delta R vector is this guy right here. So at each t, you have a delta R and you have R prime of that t. Do you guys see how the displacement vector and the tangent vector are like almost the same vector? Almost the same magnitude, and they almost point in the same direction. Okay? So what I would like you guys to note is that the delta R vector is approximately equal to the tangent vector. As the magnitude of the displacement vector starts to approach 0, those get even closer and closer, and they slowly start to become the same vector, pointing in the same direction. Okay? Okay. Now our vector field. There's vectors all over the board. We just don't see them, right? But we're going to get a point on the curve, and we're going to plug it into the vector field, capital F. I don't know which way the vector field is pointing. But let's say I plug in that point into my vector field function, and it gives me this vector. Okay. So here's note number 1. Here's note number 2. Remember that when I plug in some t into my vector function, that gives me some x component, some y component, and some z component. We're going to call them xi, yi, zi. And those xi, yi, zi are the coordinates of that point. This gives you the coordinates of the point xi, yi, zi on the curve C. Okay? You guys can see that? Yeah, okay. So this is something your textbook's going to use, which when I was first teaching this confused me a little bit. So if it's confusing me, it's probably going to confuse my students. They're going to write a composition of my vector function inside of a vector field. And that's confusing because a vector field is supposed to input a point. What the hell do you mean I plug in a vector function? So this means that you're really plugging in the point that the vector function the terminal point. That's really the point that you're plugging into this vector field. So this means that. Okay? You're plugging in that point that you got from the vector function.
So the vector RTI is a position vector, right?
It's the position vector on the curve, yeah. Yeah. And then to compose that inside of the vector field really just means plug in that point on the curve and plug it into the vector field. Yeah. and then that's gonna be R of T naught, for example. Okay? You do that for all the vectors, all these points. You're gonna get all these different, all these vector field vectors. I don't know how they're pointing, but let's just say they start changing. This is a vector field. I don't know what the vector field looks like. I'm just pretending those are the vector field vectors. Where, actually, let me erase this one. Where this one is the one you get from plugging in the point at Ti. Okay? Sorry for all the drawings, guys.
So f of r t I is to send the change of the vector.
F of R of Ti means you're plugging in the point, that point right there, into the vector field, and it gives you this vector of your vector field.
So what is the eventually?
So what we want to figure out is my curve flowing with my vector field or not, right?
Okay.
So the way we're going to answer that is we're going to say, well, what's the relationship between these vectors that are going to approximately be equal to each other? What's the relationship between these green vectors and this black velocity vector field vector? Like, how are they related to each other? And so we're going to use the dot product to tell us the angle between them. Is the angle between them less than 90? If it is, then they're relatively going in the same direction. Are they orthogonal? So then the path is like perpendicular to the vector field. Or is the angle going to be greater than 90 degrees? So that tells me that the path is going one way, but the vector field is pointing in the opposite direction, relatively. Okay? But you're going to do that, and you're going to keep chopping it up into even more and more pieces. Okay? All right. So that's it for the drawing. So much freaking drawing. So to find the relationship between the vector field and the orientation of C, what we're going to do is we're going to take the dot product of all the vectors from the vector field, these big black vectors. You're going to look at all the black vectors here, and you're going to dot them with the delta Ri vectors. All these little displacement vectors. Okay. You're going to do that at all the t's, at every single point, at all the time. So at this time, corresponding to this point, this point, this point, this point, you're going to do all that. You're going to sum up all those dot products. So you're going to do the dot product of these two, the dot product of these two, the dot product of these two, and so on and so on and so forth. Okay? And you're going to add those up from 0 to n. And then that will kind of give you an idea. Well, if all these dot products are mostly negative, right? What happens when a dot product was negative? What's the angle relationship?
Negative.
If the dot product of two vectors is negative, what did that tell you about their angle between them? It was greater than 90 degrees, right? So if you do this sum and you get a negative answer, that tells you that mainly all the vectors on the curve and the vector field are going away from each other. So that would tell you that the path is mostly going opposite of the vector field flow. But if you add them up and you get something that's positive, that means that most of those dot products have it so that the angle between those two vectors is less than 90, so it's relatively flowing in the same direction. Okay? Charlie, yeah.
So in this case, you have your answer.
In this case, your answer tells you, you would want it to be positive if your goal is, I want the path to flow with my vector field. That's when you would So the bird that was flying against would most likely have a sum that equals a negative z, because all those dot products are going to be negative. Okay. So we use this idea here to define what a line integral is going to be.
You need to go along a line.
That's right. Yeah. So we're going to say let the vector field, capital F, have continuous component functions. For a smooth curve C, right? We want it to be smooth, no crazy corners or cusps or anything like that. For a smooth curve C, given by this is a three-dimensional vector here, vector field, x of t, y of t, and z of t, where t will range from A to B, so that it gives me P and Q, where we're going to have the time here range from A to B. We're going to say the line integral, of f along C is we're going to get this sum. We're going to put that sum right there from 0 to n. So we're going to use that. But we're going to chop this up into even smaller pieces. So that means that this n is going to go to infinity. So instead of breaking it up into 10 pieces, it'll be 20 pieces, 100, 1,000, 1,000,000 pieces. As we do this, that's going to force the displacement vectors to get smaller and smaller and smaller and approach, and so that their magnitude is going to slowly approach 0, since these segments here are going to get smaller and smaller and smaller. If this limit exists, then we're going to write this as a line integral. So you guys can see it start here. We're going to say it's the integral along C, and we write the vector field dotted, instead of delta r, we're now going to say dr. Okay? But the way we're going to compute this line integral is we're going to convert it to a calculus 1 integral by doing this. We're going to compose the vector function r into the vector field. Like that. And then these dr vectors, which are the displacement vectors, as these displacement vectors start to approach 0, they start to approach r prime. So then we're going to dot them with r prime dt. This is a vector, this is a vector. What happens when you dot product two vectors? You get a scalar function, which is a calculus 1 function. And the t here is going to range from A to B. See this part right here, this composition again? I want you guys to remember that this composition really means that you're plugging in the x function into the vector field. You're plugging in the y function into the y part of the vector field, and the z function into the z component of the vector. Just the way kind of this meant you're plugging in a point. This means you're plugging in the component functions. And then just a little note here. The definition is similar in R2. It's just you're dealing with a two-dimensional thing versus a three-dimensional thing. Questions on this diagram? Anything you want to repeat? So remember the warm-up, okay? If the dot product is positive, the angle between the two vectors is less than 90, so they're relatively pointing in the same direction. If the dot product is negative, the angle between the two vectors is bigger than 90, so they're going to be relatively pointing in the opposite direction. Okay? So now just imagine every single point you're doing that. You're looking at its tangent vector and the vector field's vector, and you're taking the dot product. Every single point. That's kind of what this is happening as the limit goes to it. And then you're summing up that infinite sum of dot products. Okay. Let's play with an example. Maybe more, it'll kind of make a little bit more sense. Let's see, hopefully. All right, so the homework for this section will look like this. So let's say evaluate the line integral of f dr along C, where C is given below. Actually, let me just write it. Where C is given by R of t is just, this is two-dimensional example. Cosine of t, sine of t, where t ranges from 0 to pi over 2. And the vector field, you have to have that, is x squared minus xy. Okay, let's see what's up. Just because this is the first example, I don't want to just go straight to the integral. Let's do a little bit of visual first, and then we'll go straight to the integral. Okay. I need you guys to remember what that curve looks like. X is cosine t, y is sine t. What does that curve look like? X is cosine t and y is sine t. It's just a circle. Remember, think polar? It's like x equals cosine theta, y equals sine theta, right? It's just t. What would be the radius of the circle? 1, radius 1. So the curve C is going to be the circle of radius 1, but t, or think of theta, only goes from 0 to 90 degrees. Right? So when t is 0, what do we get for r here? What's r of 0? Cosine of 0? 1. Sine of 0? 0. So you get this point right there. You get that vector stretching right there. But it's just that point. Okay? And it's a circle, right? A radius 1. So think of it like it's going to be this curve going like this, oriented in this direction. Okay? That's C right here. Okay, here's what we're dealing with, guys. It's a little off scale, okay? But this is the vector field, x squared and then minus xy. That's what the vector field looks like, okay? And then this is the path, C. From what we just discussed, when we finish doing this line integral, do you think the answer will probably be positive? Do you think it'll probably be negative? Or do you think it'll be 0? From what we just discussed. And yeah, the curve's going this way. So what are you guys saying? Negative? Why negative? This is going an opposite way, right? So all these little tangent vectors, when I dot them with the vector field vectors, their angle is going to be bigger than 90 degrees, so all the dot products are going to be negative. And so most likely, the sum of all those is also negative. That's kind of the intuition. Okay? Yeah.
Do you use reference angles for those, or do you go all the way down, all the way down 50 times?
We're only looking from 0 to pi over 2. Sorry,
But I
to
mean,
pi.
on the line itself, when you dot it.
Oh, it's been a minute, but for chapter 12, when we talked about the angle between two vectors, the angles only went from 0 to pi. So that angle theta will only either be 0, where it's literally pointing in the same direction, or pi, where it's literally pointing in the opposite. And so yeah, so if you got your vector field vector going this way, but then you have the tangent vector going that. And that angle is hella bigger than that negative. Okay, so we're saying it's negative. Let's see what's up. Let's look at the mechanics now. It should be, yeah. Otherwise, uh-oh. I just broke math. Okay, let's see. Let's do it. All right, so let's see how we're going to actually keep this guy here. All right, let's do the construction first. So, we're being asked to do this line integral. To do the line integral, we're going to have to do it this way and turn it into calculus 1 integral. Let's see. So we're going to need to do this. Now, by definition, we're being asked to find this line integral. By definition, it's going to be f of r of t dotted with r prime. And what is t ranging from? Over 2. Okay. So, what the heck is that going to be? That's what I was trying to tell you here. You're going to look at the component functions of your vector field. This is the component function x of t. This is the y component function. Okay? This x, I'm plugging in for the x in my vector field. So wherever there's an x here, I'm going to rewrite it with the x function. Okay? So f of r of t really means that you're doing f of the x function, which is cosine of t, and the y function, which is sine of t. That's what this really means. And so that means that when you plug in into the vector field, anything that has an x gets replaced with cosine, And anything that has a y gets replaced with sine. And then this will be minus cosine t, sine t. Okay? So that's usually this is a thing. Okay? And then we have the derivative that we're going to need. The derivative of r, which is going to be, help me out here, is that minus sine? Yeah. Minus sine of t, and then
Sine
cosine. And then cosine. Yeah. So that means that to finish this off, we move it over here. We got t goes from 0 to pi over 2. And I'm dot prodding f composed with r, which is really this vector field here. This vector cosine squared minus cosine sine dotted with r prime, which is minus sine t cosine t dt. Okay. So then we take the dot product. Let's take the dot product. Help me out here. That's going to be this. Remember, the dot product is the x component times the x component. So it's going to be minus sine t cosine squared t. And then remember, it's plus with the dot product. It's the product of the x's plus the product of the y's. So this function times cosine. So I'm going to end up with actually a minus. It's negative. Sine t, is it cosine squared again?
Yes.
T dt. Questions from here to there? Okay, so since you guys said these are the same, let's go ahead and combine my terms. So we get, I think, 2 of them, right? Yeah, we get 2. So we're going to get, this becomes minus 2 sine t cosine squared t. And so let's take that negative 2 out of the integral. And so I just end up with cosine squared t. I'm going to write it this way. Like that. End up with that. All right. Anybody know what we should do? You said. What did you say? What you gonna say?
I was going to say change cosine squared t to 1 minus.
You could do that, but then you have to use a half angle. You're gonna end up doing it, I think. No. You could do that, but it won't be wrong. It just takes a little bit longer. But yeah, I think use of here will make it a little bit faster. So we're gonna let u equal what? Cosine. That way du is negative sine of t dt. Divide the negative here, so we get negative du is sine t dt. That way this just gets replaced with negative du, and then this becomes u squared, and then a negative du. So that. Take that negative out, so that way they're both positive. And so help me, now we integrate u squared, which is not bad.
1/3.
It's 1/3, so 2 times 1/3 is just 2/3 u cubed. Right? Undo the substitution. That's just going to be cosine cubed. Okay? This is 1/3. The integral of that is 1/3 u cubed. But if you plug in the cosine back, it's 2 times 1/3, which is 2/3, and then cosine cubed. Evaluated from 0 to pi over 2. So moment of truth, 2/3. What's cosine of pi over 2? 0 cubed minus 1 cubed. So there's where the negative comes in. So negative 2/3. Is that a big negative or a little negative? It's a little negative, okay? But it's negative. So but relatively, the thing is that there's times where the curve could be going with the flow of the vector field, but it's telling you that like out of the net amount, it's mostly going against the vector field, like we saw in the picture. Okay? Charlie and then Dylan. Yeah.
Indication of how against
It could be.
Same as like -1
Exactly, yeah. If it's a really big negative, then most of the time it's like really against it. Yeah, it's really against it. Sometimes you'll get 0. And if you get 0, it's like, it could be that you were most of the time, like half of the time going with it and half of the time going against it. Or it could mean that most of the time you were just perpendicular. Yeah, so it's that's kind of the interpretation. Yep.
Could you also get an accurate answer by dividing it into sections where it is similar, so that you have like one big section where it's really going with the curve, and then one big section where it's really going against the curve?
You could do that, yes. So that's one of the properties that I'm going to give to you towards the end of the class, is you can have a curve broken up into different curves, and then the line integral of that is just the sum of the line integrals. That's going to be one of the properties. So yes, you can do that. Questions on this part? This is the new stuff right here. This is the new chunk. And knowing what the answer kind of means. Okay, I'm going to have you do one. I'm not going to show you the vector field until later. And then I want you guys to make a conclusion of use the same path. We're going to use the same path. How is that path flowing in relationship to this other vector field that I'm going to give you? All right, so try this out. So evaluate the line integral along C using the same path that you were just given. Cosine t, sine t, where t ranges from 0 to pi over 2. And this time, I'm going to give you this vector field. -2y. Yeah, so try it out. Please practice this, guys. I know that your brain's on the test, but it's notes that you're going to want to use for the homework later this week. Try it out. Try it out. Some tiny little differences, not that big, but can you guys just check with your classmates? Just see if you guys have a similar kind of strategy or if you're headed in the same direction. Quick check, guys, real quick, real quick. I got 5 So what does that tell you? Seems to be going with most of the time.
Like from 0 to power 0. But 0.
As you guys are finishing up, just check your answers here, see if they make sense. This is the vector field that I just gave you with the path. Hopefully your answers are green. Anybody have a question? All right, guys, you guys can check your work here. Notice that since the vector field is just negative 2y, the x component stays negative 2, but the y becomes a y function, which is the same. Okay? And the r prime is the same r prime as this. How you do the integral could have been different. The techniques and stuff could have been a little different. But hopefully at the end we end up with 5 halves, which is positive. So that means that it's mostly flowing in the direction of the vector flow. And here's a picture. Agreeing with that. Question? Just looking up. Okay, guys. Ooh. It was 5/2. Yeah. Okay. So that's how you're going to compute a line integral and kind of its interpretation. Okay. The last thing I was going to mention is how another application of it, and then that's the last part of it. And then I'm just going to give you a handout. They're not complicated. I'm going to give you a handout with the properties. It's just 3 main properties. I'm make sure you have for your homework. So the last thing for today is talking about work. Work. So we're going to do some work here and see how a line integral comes to play. So for those of you that are in physics, how have you guys been finding work? Force times displacement? Is anyone using work with vectors yet? Force, the force vector times displacement. But remember, they're vectors. So what do I mean by times? The dot product. Okay? Yeah. So to find the work done on an object that is moved in a straight, we're going to go to like the very basics, in a straight path by some constant force. The way you've been doing it is you multiply all the force in the x direction with the displacement in the x direction, plus the force in the y direction times the displacement in the y direction. So that is where you naturally are going to end up getting that it's some force vector dotted with some displacement vector. Where this is the force being applied to the object, and then this guy here is the displacement vector. And so it would be like it'd be like if I had an object that was moved from here to here. Careful. This would be your displacement vector. It was moved from here to here, and there was a constant force that was pushing it, let's say, was moving it. It was applied and then it went here. But the path that it moved in, the object, was a straight path. Okay, then it's not too bad. You just think the dot product of those. Where it gets tricky though is if you don't have the same force acting on it, and if your path is not even a straight path. That's where it gets tricky. So if an object moved along a path C in a force vector field, capital F, okay, so let me show you little picture. So it's some path like this, from here to here. The object was moved in this way by the force vector field here. Let's say this is at time A, and this is at time B. And it's not going in the straight path because now you got forces acting in all kinds of different orientations and magnitudes and stuff. Let's say these are all the force vectors. Okay, and your force vector field here. The way we're going to find the work done is similar to what we just did with that big picture I gave you. We're going to break it up into little segments. I'm not going to do it again. We're going to break it up into little segments, and we're going to look at the force vector and the displacement vector moving within that little path, so that we can use this an infinite number of times for all those little pieces of your path. So, for example, we have a displacement vector from here to here, and then the smaller that displacement vector, the vector field vectors are relatively the same length around that small little piece. They don't change orientation much. So they're going to be kind of constant around it. So that's what we are able to do there. So we find the work done moving the point from here to the small straight path here, and then the work done for all these small little segments. We're going to find the work done. So that means you're going to do the dot product of the displacement vectors with the force vectors. Add those up, go to infinity. So if an object moved along the path C in a force vector field F, then the work done can be computed using a line integral. Where the total work is going to be the sum of all those little tiny works, which ends up being exactly the same as the line integral that we defined. It's pretty sweet. So part of your homework, they're going to start you easy. They're going to say, consider an object that moves in a straight path from some point in 3D space to another point in 3D space, like literally just a straight line. Okay? Find the work done moving the object using this force vector. So you're going to have to do it. What you need to review, which I'm going to help you, is parameterizing the line segments, which I had you do in chapter 12, which you haven't done in a while. Okay? So for your homework, in section 16.2, you'll need to parameterize a line segment. And I'm just gonna remind you real quick how to do this. You have a line segment from P to Q. P will have coordinates x0, y0, z0, and Q will have x1, y1, z1. And you want to move it this way. You guys learned how to parameterize the line going through those 2 points. You guys remember that? The line going through those 2 points? You needed a direction vector. So you needed a direction vector. In this case, the direction vector was just the vector PQ. You use those 2 points, and you make the vector PQ. You guys remember how to do that? It was terminal minus initial. Terminal minus initial. So it was x1 minus x0, y1 minus y0, z1 minus z0. And we called these A, B, and C for your direction vector. So then, to parameterize it, the equation of the line segment you use the vector function, and you said you picked the point P. No, that's how do we review the questions? Like in chapter 16. Remember, you grab the point, the initial point, and then you use the direction vector A, B, C. So it was x0 plus AT. Does that ring a bell? Y0 plus BT. Z0 plus CT. Except that you wanted to say that your t can only go from 0, which will give you the point, to t equals 1, so it ends exactly at q, where t ranges from 0 to 1. This part here guarantees that you have the line segment from P to Q. Yeah? You know, sorry. Here's the B. Had another example to do this with a line segment. I think I'm just going to leave it on my notes. Okay. Just so that it's basically a line integral, which we did 2 already. But we have to parameterize using this. Okay. You guys want to do it?
Is there a special reason why we have to parameterize it, or just because it asks?
Oh, great question. There's the reason you have to parameterize it is because when you want to compute the line integral, you need R. If you don't have this R, then you can't do that composition. You can't even do the line integral. So for some of the problems, they're gonna bring you back to chapter 12, and they're gonna have you parameterize things the way I had you do it before. I didn't hear an answer that. All right, we'll do it. We'll do it. But I'm gonna have you guys do some of it so that I'm not just up here talking. So we'll do example/practice. Okay. Yeah, we get there. All right, so the homework question will look like this. Find the work done by a force. I'm going to call it force field. It sounds cooler. It's like Star Wars. or the force field F, it's going to be three-dimensional. The component for the first component will be x plus 2yz. Then we have 2xz and then 2xy. So find the work done by force field that moves an object from the point P, coordinates 0, 1, 3, to the point Q, 1, negative 10, 1. Okay, picture this picture here. You got P, the point starts here, and through the force field here, it ended up moving it up to here with Q. What would be the work done by doing that? This is a negative 10, yeah. Yeah, 1, negative 10, 1. Yeah. And so as I mentioned, to do the work, I need to do this line integral. But I need my R to start doing this, which I don't have. I have my vector field F. I don't have R. That's where Dylan, your question comes in. That's why you have to parameterize that line segment. It doesn't even say line segment. You need to understand that it's a line segment that moves it from P to Q. Okay? So to do this guy, we need to parameterize the line segment PQ. And so we're going to do this review here. So do that real quick, guys. Parameterize it. We'll continue as a class, but I just want you guys practicing this. Parameterize. The direction vector PQ. Yeah. So this is the part that makes sure it's a line segment from P to Q. Okay, that's what guarantees that it'll start at P, and when you enter 1, it'll end at Q. All right, let's keep going as a class. What did you guys get for the vector PQ?
0, negative 10, negative 2.
10, negative 2, perfect. I know you guys were totally asynchronous. Yeah, so this is the direction vector. This is the A, B, and C when you're parameterizing it with R. Okay? What's your X naught, Y naught, Z naught?
1, 0, 2.
Yep, 1, 0, 3. So then therefore your R is going to be, it's going to be 1 plus 0t. I'll just put plus 0t here for fun. And then 0 minus 10t, and then 3 minus 2t. And so your RT becomes 1 negative 10t and 3 minus 2t, and then because it's a line segment, it's always going to go from 0 to 1. Okay? All right, so let's see. So I'm doing the work here. I'm gonna compose R inside of that nasty vector field. Take the derivative of R, and then dot product that. Now I know T will go from 0 to 1. This vector field kind of scares me, but it actually works out really nicely, okay? So let's see, hold on. So if this is my R, this is the X, everything that has an X becomes a 1. Everything that has a Y becomes a negative 10t. And everything that has a Z becomes a 3 minus 2t. Okay, that's how you're gonna do that. That's kind of why I wanted to do this problem, because that part is good. It's good for you guys to see that. So this tells me that f of R of t is going to become x, which is really now 1, plus 2 times what? The y, right? Which is the y function. Minus 10t times z, which is 3 minus 2t. That's the first component. The second component is 2 times x, which is 1, times, what is it, z, 3 minus 2t. And then the third component is 2 times x, which is 1, times y, which is minus 10t. I know, it's gross. Which simplifies to 1 minus 60t plus 40t squared. Did the math there for you guys? 40t. Oh, I said 40t. Sorry. 40t squared. 6 minus 4t, and then minus 20t. What is the R prime? Take the derivative of each of those. 0, minus 10, and then minus 2. Hell yeah. The 0 is going to be good for us. Yeah, 0 is going to be good for us. So then now when I put this here, I'm going to continue over here. So I got from 0 to 1, and I'm taking the dot product of, yeah, I'll just rewrite it again. T plus 40t squared, 6 minus 15, 40. 40, and then minus 20. That's f composed with r, and then 0, minus 10, minus 2. Hell yeah. Look at that. 0 times that whole ass number. Gone, son. That's good. That's gone. And then you just end up with this times minus 10. And when you simplify everything, it becomes 80t minus 60. Yay. Okay. Work that out, and it becomes minus 20. Okay. What is that? What do you think that tells you? It's going against it. So the work that was being done was going against it. Okay. Which is kind of similar to what we've been saying. You have more of a physics stuff in this. Okay, guys. So as I promised, yep, 3:15. Right in the money. There's just 3 properties that you're going to want to use. You don't have to look at it till you start your homework. I know right now your brain's on the exam. Good job, guys. Your energy is low and you still keep going. I love it. Thank you. Be patient with me. And the compound.
All the real world things. I want to do it in a big
Oh, you didn't get one, I'm sorry. All right, guys, I do have to go. I have to go straight to a meeting right now and update the